Okay, hello. In this video, I'd like to talk about our first application of the magnetic force that we talked about last time. So let me start off with this demonstration. I have here what's basically just an empty plastic shell. It's sized just right for a D battery to go in, but it's just plastic here, and I'm going to add to it these metal pieces here. Okay, so these are conductors, conductive metals, and they slide in from underneath so that they stick out of the top, but they're also still exposed inside. So I'm going to do that on both sides. And now I'm going to take a battery and put it inside. And so now the positive end of the battery is in contact with one of these metal strips. The negative end of the battery is in contact with the other metal strip. Okay, the next thing I'm going to do is I'm going to take this coil of wire. It's wrapped about 10 times or so, but it is a single piece of wire. Okay, now if I put this wire on here, if we think about this for a second, I think you will agree that there must be a current going through this wire right now. This one end is touching the positive end of the battery, one end is touching the negative end of the battery, and this is my conducting pathway from the positive to the negative. So I should be getting a current through this wire right now. And I can verify that if I leave it on here long enough, this wire is going to get pretty warm, just from the resistance, from the electrical resistance. All right, then there's one more piece that I'm going to add to this, is this little disc magnet. All right, so there's a little slot for it to fit in at the top. Okay, and now I'm going to put the coil on, and we'll see what happens. Okay, so here we go. Got the coil on there, and I'm going to turn it until I feel something happening, and let go. And you may or may not be able to see this very well depending on the refresh rate and resolution of my document camera here, or my webcam, but this thing is spinning. And it's still going. Going and going. So let's talk about this. Let me put it under the document camera and see if you can get a good view of it there. Okay, so here it is under the document camera. You're looking down at it now from the top, and you can see that this coil is still spinning. So this is something that you can buy in a toy store. I bought this one, and it's called the World's Simplest Motor. So I want to talk about why this works, and I also want to talk about why they call it a motor. And it's for ages 8 and up, so I guess I qualify. Okay, so here's my cartoon drawing of the World's Simplest Motor. And let's review what's going on here. So I have this battery down here, and it's connected to these metal strips on the sides. One strip is in contact with each end. And then I have the wire sitting up here in these supports, the metal strips, coils around a few times. And so let's think about the circuit that we've created. So here's the plus end of the battery. We're going to be using conventional current. We're going to be using conventional current most of the time from now on. And remember that conventional current comes out of the positive end of the battery, and it goes into the negative end of the battery. So what does the current do when it gets up here? It's going to go this way. When it gets to the coil, it's going to start wrapping around the coil. The current's going to follow the coil. I don't know whether this coil is wrapped clockwise or counterclockwise. Turns out that it doesn't matter. So let me just pick one. Let's say that it's going counterclockwise here. So it's going around in this loop. It's going to go around here, I don't know, about 10 or so times. And then it's going to emerge over here and then travel down this metal strip to the negative end of the battery. So that's what our current looks like. Okay, and then a crucial piece is this magnet, this disc magnet. And again, I don't know which end of the disc magnet is north and which is south, but it turns out that it works either way. So let me say that this is the north end and this is the south end. And so what does the magnetic field look like for this disc magnet? Well, as a reminder, if I have a small magnet, say a small bar magnet or disc magnet that has a north end and a south end, I have magnetic field lines coming out of the north and going into the south. And then I have some that wrap around. Okay, so they come out of the north, wrap around, go into the south. Okay, so we're going to have a similar pattern up here with our disc magnet. I'm going to focus, just for simplicity, I'm going to focus on this region right here, where the magnetic field lines are mostly vertical. Okay, so I'm just going to focus on a few of the magnetic field lines that are vertical, just to simplify the analysis here. So I have, say, one that's coming straight out, and then almost straight out, and almost straight out. Okay, so they're my magnetic field lines coming out of my magnet. Okay, so let's look at what's going on here. Now I have a current that's traveling through a magnetic field. And as we talked about last time, a magnetic field will exert a force on a current because a current is made of moving charges and magnetic fields affect moving charges. The formula is IL cross B. That's the formula for the force on a current due to a magnetic field. I is the current, B is the magnetic field, L is the length of the wire that's inside the field, and it has a direction, and the direction of L is the direction of I. So this is a cross product, and since it's a cross product, we can use the right-hand rule to figure out the direction of F, okay, since we know the direction of I and B. So the direction of I, let's focus on this point right here. The direction of I here, imagine that I is the tangent to this circle as it goes around. So I is going this way up here at this 12 o'clock position. All right. And what's the direction of the force? So using my right hand, I have to point my fingers in the direction of L and then rotate my hand so that B comes out of my palm. Okay, so fingers go in the direction of L, which is the direction of I. Okay, I'm going to move my hand so it doesn't block it, but I'm doing this point at the top here. So my hand is pointing this way. I need to rotate my palm until the magnetic field lines come out of my palm. Okay, and where's my thumb? My thumb is pointing into the page. So up here, I have a magnetic force on this current that's going into the page. All right, now let's focus on this point right here. So now the current is going this way. And imagine the tangent line. And so what's the direction of the magnetic force? All right, so again, with my right hand, I need to point my fingers in the direction of I. And I need to rotate my hand so that the B field lines come out of my palm. And my thumb now is pointing out of the page. So here I have a force coming at us. And here I have a force going away from us. And so look at what this is going to do to this coil. It's going to push the top end away from us and pull the bottom end towards us. It's going to cause it to rotate. Right? This is actually a torque that the magnetic field is applying on this current. Okay, here we are, back to the demonstration. So we have this coil that's spinning because the magnetic field is applying a force on the current, and it's applying forces that are going to cause a torque. Now, if we look at this arrangement, if I take away the magnet, but keep everything else the same, this thing will no longer work. I will get a current when I put this wire here. I'm going to get a current through this wire. But without a magnetic field to apply a force on this current, it's lifeless. Okay. Similarly, if I take out the battery and put in the magnet, it's not going to do anything here either. And I do have a magnetic field coming from the magnet, but without a current going through the wire, the magnetic field doesn't have a current to apply a force to. Okay, so we need both the magnet and the battery. So this is a nice example of something that is electromagnetic. It has both electrical and magnetic components. Now, this is called the world's simplest motor. Let's talk about why that is. Okay, so to give us some insight into why this is a motor, let me get it started and then ask you, by the way, it kind of climbs up one side because I don't have this thing perfectly horizontal, which is why I keep nudging it over to keep it in the middle. So when is this thing going to stop? Well, it'll stop if we take away the magnet, like I pointed out, or it'll stop if we take away the current. When will the current stop? Well, the current is going to keep going until the battery runs out. So this thing will spin until the battery dies. So what's happening here to the energy is that we are taking electrical energy from the battery and we're converting that into mechanical energy because we are making this thing move. Okay, it has kinetic energy. Okay, so we can take that as the definition of an electric motor. An electric motor is something that converts electrical energy to mechanical energy. Now, we normally think of a motor as powering something. We could, in principle, use something like this to power something. Since this wire is spinning, you can almost imagine it's like an axle. I could put a wheel on each end, right? And now I've got wheels that are rolling in one direction or the other. Okay, there you have it, the world's simplest motor.